drivers, how do you determine which map into a set of trustworthiness? This becomes, a big problem. So this code diversity problem is a big issue. There's also a lot of operating system state, so with regards to configuration files. So Windows performs 20,000 to 50,000 registry reads during the booting process. Okay, so this is a big problem, and the state information is not useful if the configuration changes after the measurement. So if you have these changes going on, this becomes a problem. And so that's why we were looking at taking the approach where we have a static image, a read-only image that we're not expecting it to change. So if there are any changes that are going on in memory, we can detect what's going on. So we define what is trustworthy. We limit that. We allow you can, even with the plug and play, you can drop other applications within the system and make it a part of your static image, but specifically what you're running on. So that's the benefit of, having like this plug and play system. It builds the system for you. Now, whether that system is trustworthy, that's another issue, but you don't have this problem. We've gotten rid of the problem of code diversity. There's some related work on this by St. Clair et al., and it's called RODI. It's a root of trust of installation. And what they use a virtual machine along with this static image to actually do this. But we're not using a virtual machine. We're actually using VM-Knoppix and the other TPM tools to actually do something, that's similar. And we're adding the secure communications channels using the TPM, and its private keys, the keys that are protected using the TPM to establish that secure communications channel. So our cryptographic keys that are used for communication and establishing the secure channel are not stored openly on the host. Okay. So with PlugNPlay Trust, the goal is to enable remote parties to verify the integrity of embedded communication systems, thereby limiting the effects of malware in a compromised system. So we just want to limit what malware can do. If we detect, we may not be able to detect it early enough that, there isn't some vulnerabilities to compromise, but if we can detect it, at least we can identify that this particular machine has a problem, and you can deploy someone to actually go and address, you can shut down the system, you can ignore requests from that system, and those are the kind of things that you want to do to be able to limit it. Okay, this system is compromised, but our entire system won't be compromised. And this is specifically important if the malware is using the network of nodes to propagate itself, throughout a whole banking institution, So this becomes a problem. So if we can limit the effects of the compromise, we may not be able to prevent it, but we can detect and limit, and that's what we're trying to do. So the system provides remote attestation. And we didn't create TPM. We did not create, the interface to the TPM. Those tools were there. But what we did do was integrate those, and provide a remote attestation application, the validation application, and the firewall service at the application level that utilizes those things. So, and in the secure communications channel, we have OpenSSL actually integrated with the TPM. So those are the things that we've actually, done. So you are not concerned about your keys being stored on the host in an unprotected state. So when we're looking at trusted state, to trust a system means to trust all the files on that system, including binary and configuration files. For a system to be trusted, it must be identical in every way to a predefined trusted baseline. So this is certified trust for integrity purposes. So that's, that is what we are trying to achieve here. Okay. So how we're actually doing this is that we use a trusted platform module as our hardware notion of trust. Okay. it gives identity verification and remote attestation support. So when you look at the TPM, one of the things that it's easily used for is for identity verification. Basically, I have a cryptographic identity and endorsement key that's stored within the TPM. I can create multiple other identities. The vulnerability is that if someone gets hardware access to the device and they open it up, they can gain access to the keys. And when you look at earlier versions of the TPM, you could actually reset the TPM just with a wire. And so those issues were addressed in later versions. So in 1.1, it actually had, that particular issue. Like, how can I, if I can easily reset the TPM, then that makes the keys in itself vulnerable. And so those problems were addressed in like version 1.2. So those were some of the earlier issues that we had. So the other approach was to integrate TPM tools, OpenPTS, which is some work out, I think it's out of Japan. Trousers is work that's done by the Trusted Computing Group. And the integrity measurement architecture is used, in order to enable like the TPM communication. So these things we did not implement. But what we did was we used those to facilitate the attestation service and to request a quote meaning a measurement, and to also request to validate a quote. So those were the tools that we used, but first thing we had to do was just integrate this and get it all to work. The only other, I teach a class in trusted computing at Indiana University in Bloomington. And so what we've been lacking is just a platform to actually do this kind of research. And so there is like a trusted computing emulator, but some of the work has not, it doesn't implement the full specification, the full TPM specification. So some functionality was not there when I tried to use it a couple of years ago. So actually just having this in place, becomes very helpful, because now we can look at, what types of problems can we address without having to be concerned about, do I even have the basic platform to just do this kind of research and evaluate the things that I'm doing. Like, even if I have, let's say for an example, an electronic voting system, where I'm relying on, let's say for an example, it's written in Java. So now I have to look at the Java runtime environment. What does it mean to actually take a measurement of that? Can I efficiently do this in, using the TPM? I can't even answer those questions if I don't have the basic platform that I can readily use. And this is what, the PlugNPlay Trust allows us to do. So, and we use live CD technologies, VM-Knopics, to create a read-only system of the certified distribution. And basically, reason we did the read-only, because we didn't want to have to address the code diversity problem, and what we envision with embedded systems is that the software stack is smaller than on our regular laptop. So one of the problems that I was talking with today with Dr. Bertino is being able to ask the question, can I trust my own laptop? I can't answer that question. I want to be able to answer that question. Can I answer that question with a trusted platform, using a trusted platform module to measure the integrity? I don't know. And the reason I don't know is because the system is so large. There's so many things that are changing, and is a change malicious? Or is the change acceptable? That is a very hard problem when you're dealing with the amount of code and the amount of things and the amount of state that can actually change. But those are some of the things that I would like to do. Now, there is some work in the area of like attribute-based attestation. So what that does is, what you try to do is map this larger set of state into a smaller set, into some specific attributes. And then you measure the system based on the attributes. And there are a couple of, there's more work in this area, but it's really at the beginning stages to try to address the code diversity problem. Okay. So what we provided basically are